Every year I try to have the weirdest presentation at the symposium. I'm not doing that this year, so I just went with the weirdest title. All right, so we are going to be talking airflow and focusing on the fundamentals of basically what causes airflow and what causes bad airflow and good airflow. So first thing I always like to talk about going in is something that you probably already have an understanding of, but can be hard to understand the scale of, right? Size matters when it comes to ductwork. And it's because it's not the difference between a 6 and a 7, right? You think in your head 6-inch versus 7-inch, you're thinking of a certain disparity, a certain delta. But a 6-inch and 7-inch, those are linear measurements. So when you're talking about area, cross-sectional area, which is what the air has to go through, right? The air doesn't travel in a line through the duct. It travels through the whole duct. So the difference between a 6 and a 7 is a 28 versus a 38. It's not a 17% change. It's a 36% change. So it's really easy to look at something and go, I mean, come on, it's supposed to be a 7, they got a 6, it'll be fine. Because 17% doesn't sound like that much. It's not 17, it's 36, right? How you size a duct matters. Duct sizes increase on the red line, not on the blue line, right? It's on the square, it's geometric. Okay, so this is where the David Bowie part of the title comes in. We're gonna talk about pressure, okay? Static pressure, velocity pressure, pressure loss, external static pressure. 4 unique concepts. And most of the time in the HVAC world, we just say pressure. And it's no question, there's no question whatsoever as to why this can get so confusing. If we're gonna use one word to mean 4 different things, you are going to get confused, right? So first of all, pressure's not the bad guy. If you don't have pressure, you don't have airflow, right? Pressure is the one doing all the work. Pressure is the reason we have airflow, right? We often say when we have airflow problems, we have too much pressure. Well, no, you don't have enough. You have too much static pressure or back pressure. But if you could create more total pressure, you'd have more airflow. Airflow is doing the work when we're talking, pressure is doing the work when we're talking airflow, all right? Friction is the bad guy, okay? Friction is the reason you're not able to do your job and deliver the airflow you're trying to deliver, not pressure, right? So understanding pressure is pretty darned easy, right? I like thinking in terms of PSI, right? Pounds per square inch, right? Tells you exactly what pressure is. It's a force spread over an area. Friction, anytime you have resistance to anything, that's friction, right? They talk about friction in financial markets. Anytime you're trying to do something and something's trying to stop you, you could call that friction, okay? So it is really common to think that the airflow somehow is caused by like how much room there is in that opening, right? It has nothing to do with that. It's just accumulated friction. And it can be really difficult to sort of, in your head, identify the actual problem as being this. And so one of the primers I like to just throw out there when we start talking about this is imagine an asteroid the size of a Volkswagen Bug, okay? About 20 of these per year come hurtling toward Earth, right? None of them hit the ground. They burn up. A giant rock and metal object comes flying to the Earth. The only thing that burns it to a crisp, vaporized, is the friction of the air moving across the surface, right? It's the same thing at play in a ductwork on a ridiculously smaller scale, right? It's the friction of the air moving across the surface or changing directions, right? We'll get to that in a minute. So Ty Branham and I have he's my man. He's my mentor, if you will, or my idol. Idol's a better word. Being able to visualize what's happening is really key to understanding. And air's invisible, which sucks. So if you want to understand pressure, maybe we should understand something a little more physical, a little more tangible, like a giant crate with a bathroom scale attached to it. If you pushed on the scale and you were on a low friction surface, like a sheet of ice, it will move away from you pretty easily. And what's going to happen to the number on the scale? Not much. Because you're putting energy into the system and it gets used. It moves. The number on the scale goes up when the energy gets wasted to friction, right? And so when I push on it, it just flows away from me. The scale number doesn't do anything. If we put it on gravel, we can get a very different result, right? We could push the same amount, and it's not going to move very far. But that scale number is going to go way up, okay? Yeah, just physical normal sense, right? The same thing is happening in a duct, okay? We have the energy we use and the energy we don't use. Our job is to move air, right? When we're not doing our job, the air is doing something else instead of moving. It's being deflected, right? So I kind of need two hands for this little demo, but air isn't going to go in two directions at the same time, obviously, right? Or two opposite directions at the same time. We can't have that in the duct. So if I have a force going this way and a force coming this way, this force coming here, if it's the losing force, friction is the losing force, it gets deflected at 90 degrees. It pushes outward, okay? And a lot of you know this. We have names for that. It's velocity pressure, static pressure. Velocity pressure is the energy we're using. Static pressure is the energy we've lost. We've lost it to friction, okay? So pressure is always in balance, right? Pressure, engineers like to say pressure is always equal. Oh my God. I taught people how to do manual D. And I was teaching them how to do manual D. I followed the process. I had no understanding of what was actually happening inside that duct system. Legitimately, I didn't understand this until I got tricked into doing a presentation to a room full of engineers. And they didn't tell me they were engineers until the night before the presentation. It was the last time in my life I pulled an effective all-nighter watching YouTube videos trying to learn how this works. And when I figured out that pressure is not equal because it's the same here as it is down here in the duct, pressure is always the same, or always in balance, excuse me, at that point. At one point in the duct, you've got a certain amount of energy. Whatever you're using to go forward, you're not using to push outward. Whatever you're using to push outward, you're not using to go forward. These two things are in balance. It's one of those things where turning it into an equation is almost silly, right? This is just what happens. Of course it does, right? You can't use more energy than you have, and you can't use less. That's it. That's all it means, right? And so we have two oppositional forces here, right? If you have larger duct, you have less friction. Smaller duct, you have more friction. And then you get the pressure side. Pressure's moving the airflow. If you have more pressure, you're going to have more airflow. You have less pressure, you're going to have less airflow. So this is Mr. Static Pressure right here. It's silly, I know it. But if you want to understand static pressure, this is where the used car lot comes in. Legitimately, sometime after I did an all-nighter watching YouTube videos on pressure, I was sitting next to a used car dealership, and one of these guys was going. And it just randomly occurred to me that this is probably the best demonstration of static pressure and velocity pressure being in balance that you can see, okay? When he's like this, all the energy is velocity. And so this one actually, I should have tested it before I brought it up here. The fan's a little overpowered on this guy. He doesn't like to dance so much. I have a different one I should have brought. He's just too small. Because oftentimes if I hold him up just like this, he'll sag. You can literally see the inward collapse of the tube. But I don't actually need to hold this guy to make him stand up, right? He'll fall over because when the energy is being used for velocity, it's not being used for static. So obviously he's puffy, even when I do this, but there's just less energy pushing out, which is why he falls. I can make him stand just by putting my hand over the top of him, right? Because if I create some resistance and I get less velocity, I get more static. It pushes outward more, right? And if I take it away, he falls over, right? Silly, I know, but you'll never pass a used car lot without thinking about it. So we measure pressure basically one way, right? We use different tools to do it. This is where the 40-cent tool comes in. I literally had some vinyl tubing that I totally left at my house, yeah. But you can build a manometer with 40 cents worth of tubing. Like literally, you plug one end into a duct and the other end open to the air, and you put some water in it. However many inches of water column, or how many inches it moves up from baseline, that's inches of water column, right? I like PSI as a way of understanding what pressure is, right? Force over an area. I love inches of water column because it shows you what it does, right? It literally pushes that water up the column. As much as I love digital gauges and better tools, man, sometimes it would be nice to like start with some real low tech, right? And we moved to dials, of course, and then we got these things that measure things all the way down to pascals, right? Which is a fraction, 7,000th or something like that of an inch. Then you get this thing over here, which is supposed to be a pitot tube. It's not the best drawing of a pitot. It's better than the one I had before this. Pitot tubes are how you measure velocity. And the first time I met Jim Bergman was at a presentation like this. I said what a pain in the ass it is to measure velocity pressure. And Jim was in the back of the room and he said, "Not if you have the right tools." Okay, tell me what the right tools are. And I got an education on how to properly do velocity pressure measurements. And one of the key tools is something that can take a transverse, take an average. I got to be able to hit a button and let that tool do a whole bunch of measurements as I drag that tube with the tip pointing toward the flow across the duct. Because air is moving at completely different speeds in that duct. The air around the surface, where it's in contact with something and experiencing more friction, is actually moving slower than the air in the middle. And by the way, not all of that air is going exactly the same direction. So, in short, measuring velocity pressure is a pain in the ass. Which is why everything we talk about in the HVAC industry is static pressure. It's just easier to take the measurement, right? That pressure is pretty uniform, especially if you have a round duct, all the way around that point, right? You'd have to be putting the probe in at like the corner of a square duct or something to get a bad static pressure reading. It's easy to do, right? But before we know it, static pressure is the only way we think about pressure, and then that just becomes pressure, and then what are we doing again? Velocity. You guys don't actually care about static pressure. You think you do. You care about velocity pressure, right? Hydraulics engineers, they care about static pressure. If they F up static pressure, something blows up, okay? I've only seen a picture of one duct system where they swear it blew up from static pressure. I still am not 100% buying it, but okay, right? Velocity pressure is our job, not static, okay? So why do we use static so much? Well, because if we're gonna control our airflow, we can control our pressure. That's just the blower, right? How much power do we got? Or we can control friction, okay? And friction actually comes from multiple sources. It's not just the surface of the duct, right? So you might have some smooth, like metal duct. You get a little friction from that. You might have some flex duct, which, by the way, not the devil, right? Flex duct works great if you account for the fact that it creates more friction. You just need slightly bigger ducts, right? Because they're gonna create more friction. I can create the same friction with a flex duct this size as a sheet metal that size. But where most of the friction comes from is actually the fittings, the changes in direction, right? It doesn't even have to be a fitting, it's just a change in direction. If you have a piece of flex duct and it's got a turn in it, we're gonna call that a fitting for the purposes of this conversation, right? When the air is moving in a new direction or changes direction, it's gonna create more friction. So we have a term that we use in Manual D, it's called equivalent length. You actually use it all over the place, it's engineering. It's a really simple concept. If a fitting creates the same amount of friction as 80 feet of straight line duct would, it's an 80-foot fitting. Now, that may be in somewhat fine print down there, right? There's a really big print version of this where it's at a certain friction rate and at a certain velocity, okay? This, with the actual mechanics are happening here, the actual math, I hate doing the math, right? I don't need to do the math. They have calculators, they have software, we can get that stuff. The actual math is a lot more complicated than that, right? But that's how we do things, that's how we estimate the effects on flow, okay? So it turns out that in residential, it's a little easier or a little more realistic to expect to be able to manage friction than it is to manage pressure. Because this is my blower, and it's pretty much the one I got, right? And so I need to manage something, and I forget what business guru said it, but you can't manage what you can't measure, right? So how do we measure friction? There's no such thing as a frictionometer. Okay, that doesn't, right, TEC? No such thing? Okay, just making sure. They would probably have one if somebody did. So in order to quantify, in order to measure, in order to control our friction, we actually use pressure measurements to do it, okay? So if I have a magical duct with no leaks, where's Doug Crawl? If he's around here, he'll make me a duct with no leaks. He's good at that. And if there are no leaks in this duct, right, with all the gores on that fitting, that's kind of tough. If 100 CFM goes in, 100 CFM is going to come out, okay? Has to. If less air came out, it would eventually explode. If more air came out, it would implode. Those two things don't happen, so 100 in, 100 out. Took me a while to realize why some people have a little bit of trouble with this. They often think of the air hitting that fitting and slowing down as a result. Okay, I get that. I like to think that those people are thinking of airflow as a race on a track. The cars start at the starting line, they start driving, they encounter the corner, and they slow down because of it. The problem is there's already air in the duct system the moment the blower starts. It's not a race, it's a traffic jam, okay? If we all parked our cars on the highway at night, and in the morning, all walked out to the cars, and at exactly 8 a.m. started the cars and started driving, you're in the traffic jam already. Whatever problems there is to the flow becomes your problem. I don't care if you're 10 miles back. So the same thing happens here. You experience that friction almost instantaneously. It might actually be instantaneously. I don't know the physics well enough to tell you that, but it might as well be. So we're going to encounter this friction. We're going to get the same airflow from one end and the other. Now, important to this is the duct isn't changing sizes. The reason that's important is what we're going to do is we're going to measure static pressure, okay? If I have a certain amount of energy at the beginning and I have less energy at the end, and velocity pressure and static pressure are always going to balance out, where's that disappearing energy going? Because it's not being lost to velocity. There's 100 CFM coming out of it. It's got to be going the same, important word here, average. It's going to be going the same average speed, okay? So the velocity pressure didn't change. That means all of the change happens on the static side, okay? Static pressure loss or static pressure drop. You've heard the term before? Yeah, it's a measure of friction. It's exactly how much friction there is between those 2 points. If we have the same velocity, whatever energy you lose to the static side is however much energy you lost the whole way, okay? So when we use pressure losses or pressure drops, that's what we're saying. We're saying there's this much friction happening across that coil, across that filter, whatever it is, right? There's a reason you can't take a static pressure reading in the supply plenum and in the branch and know anything useful, okay? Because they're completely different conditions, right? Different amounts of air, different velocities, different everything. You have to isolate a variable to get something useful. And so as long as we're moving the same speed and as long as we're moving the same speed would work, but as long as you have the same amount of airflow and the same size, the pressure difference between those things is measuring friction, okay? So that's where this thing comes in. All right, guys, what number should we use? Anybody want to just throw, you know I'm just going to shut it down, but okay, I'll spare you. There isn't one, okay? There isn't one. Yeah, there's a little marker on it and everything. My instructor. So, fun fact, little bit about my background, which I skipped. I was the head trainer for RightSoft for many years. Brace yourselves, everybody. I've got a degree in English communications and philosophy. And 20 years of experience teaching people how to design stuff, and a curious mind. I did not like teaching people things that I didn't understand, and so I tried to understand them. And duct was the last piece for me. It was the last thing that fell into place, for sure. And I paid, and this is part of the reason, good money out of my own pocket, right? I started at RightSoft. They hired me as a temp. I just wouldn't go away, right? I paid money out of my own pocket to go to a class on a Saturday to learn 0.08 is a magic number and will always tell you how much airflow is in a duct. No, not even close. I went to another class, got taught the same thing. This time I could ask questions. I was like, wait a minute, isn't a longer run going to give me less airflow? Right? Aren't there certain fittings that are going to cause less airflow? And the instructor did what a lot of instructors will do when they're asked a question they don't know the answer to. They give you a confusing answer. So hope you shut up. He said, well, it's per 100 feet. Well, that shut me up. I didn't know what the hell that meant, right? Is every duct system 100 feet long? Why? Why 100 feet? I got to guess. Because 10 feet wasn't long enough for Willis Carrier to measure the difference in the column of water he was using. He didn't have a DG8. He had a tube of water. And he was going to use 1, 10, 100, 1,000. He was going to use something that you could divide by 10 because he's an engineer. So, per 100 feet. And thus shall it be forever and ever. But it doesn't mean anything special. There is nothing special about that number. 0.1, 0.08, 0.06. You put a gun to my head, you make me pick, I'm going to say 0.06. Why? Because if a duct is bigger, I can close a damper and get less airflow. Resistance, friction, cheap and easy. Pressure, expensive and difficult, right? You want more fan power. Well, I hope we're not on the highest fan speed because you might be out of luck. I want more resistance. Man, at one point, RightSoft was owned, the company that owned RightSoft also owned a sheet metal company. And talking with those guys, they told me that when they punched out the round hole in the back of their boots, that's usually a piece of scrap. And then some of the customers started asking for those blanks. And they started selling them in packets of 100. Why? Because when there wasn't an accessible damper, guys would take the little blank, they'd fold it like a taco, and they'd reach it up inside the duct and create a damper. I'm from Massachusetts. Something that most Southerners don't know about Yankees is we love a good hack. Absolutely love it. I heard that, I thought it was great. I know most of you are like, that's bad craftsmanship, but it worked, right? Friction is easy to create. So when you do a residential duct design, you're working backwards, which is why it feels weird and wrong. You wouldn't notice it as working backwards, right? If I was talking to somebody who had never done a duct design before, never learned anything about airflow, I wouldn't be talking to them like this. I would just tell them that static and velocity are always equal and talk about friction and here's how you do it. The problem is, and the number of times I got paid to go to somebody's company to teach people about airflow, and the owner or manager would say, don't worry, I give him a little primer. Oh God. What did you teach him? Well, we broke out our Ductulator and I showed him around oh geez. All right, we're gonna have to undo all that work, right? Because they get you thinking about this from the pressure side of it, because that's what this is. There are two ways to control airflow. You can control the pressure or you can control the friction, right? Another way of looking at that is you can control blower characteristics or blower selection or duct sizing. In commercial, if I need a different motor to get more power, I'm allowed to do that. In residential, you're not, right? If I need to change pulley configurations and all that, I can do all kinds of cool stuff to a commercial system. If you need more power, you just get it, right? Commercial duct design feels weirdly arbitrary. You sit down and use 0.1. That thing they taught you, 0.1, yeah, you do that. You just take 0.1, you do a bunch of math. But there's a whole process that's supposed to come after that, right? You're supposed to use that 0.1 in the Ductulator to quantify how much friction you're creating with the length of duct you're running, okay? And it's per 100 feet, it's 0.1. If I had 120 feet of duct, it'd be 0.12 inches of pressure drop. That's what it tells me. That's what friction rate is for. So I could document that. I could write down 0.12 inches pressure drop. And something magic happens when you've already decided what size to make your ducts. The thing that I was telling you about those fittings, you need to know the velocity and the friction rate to actually know literally how much pressure drop there is. Well, if you just decide ahead of time, I'm gonna make the duct that size, you know those things. There's a little database online, ASHRAE has it. You can calculate the pressure drop, not equivalent length pressure drop, of every fitting. And you could do something crazy, like write it down, right? And add them up. And then you have things like coils and filters and other things that cause friction, and they have data. You can go and look up if I move this much airflow through it, or if I move the air through it this fast, how much pressure drop will there be? And you can write that down. Then at the end, you add it all up, and that's the blower you need. Done. That's the goal. When you start with 0.1, when you start with the Ductulator, you're supposed to end by changing what you do with the blower to meet the needs, right? You know how much friction you have, you adjust your pressure so that you achieve the right balance. Technically, it's the right imbalance, but 601, right? In residential design, you're stuck with your blower. This is it. This is the one I get. And customers have budgets, nasty little budgets. Yeah, we hate those, right? We can't just buy the best thing out there. Well, some of us can. You guys are picking your clientele, though, pretty hardcore. So you have this blower, and it can do so much. And that's all it can do. And they're not all created equal. And side note, the thing that's on the nameplate on the unit, garbage, okay? I'm convinced it has something to do with like liability or something. Because there's a table in the data that tells you what the actual airflow will be at this particular speed at a certain amount of, it's called external static pressure, right? This is the amount of resistance this fan can handle. This is ESP, or external static pressure, is a measurement of fan power. And it's something you just look up. So you do that instead. Instead of deciding what size ducts to start with, you decide what blower you're gonna start with. Okay, you take that, and you do the same thing. Stuff causes friction, right? And there's certain things that I can predict. I know how much air is gonna go through my coil and my filter and some certain other things. So you subtract that, right? This is how much my blower can handle. It's gonna have to move air through a coil and a filter. Here's how much is left, right? They give that a fancy name, it's the available static pressure. It's just what's left. How much energy do you have left over to move air through the ducts? That's what it is. And so you measure those ducts. How many feet of duct do we have? So we can do a little bit of fancy math here. I'm leaving a concept out of this, the worst case run or the longest run. It's unnecessarily tricky for just understanding the principles of airflow. But long story short, it's the fittings that get you. So something that's got 4 elbows in it versus a country mile. I design duct systems, side note. I design duct systems. If by some miracle there's a homeowner watching this, I don't design duct systems. You didn't hear that. I design duct systems. I won't work for homeowners. I'll work for you guys if you really want. And I'll probably try to talk you out of it and give you somebody else. But when I design a duct system, I get a lot of, terrible pun, back pressure from my customers. Because if you're gonna give me a stupid place to put the air handler, which they always do, not you guys, right, the architects, I will run a straight trunk that is 3/4 of the side of this house and just run really long branches to the other side. Now, I don't have to pay for those materials, so I can be, I can see reason, I can be talked to, but people look at that and they go, those runs are too long. Yeah, well, if you took 2 elbows to get there, they'd be even longer than the extra 10 feet I add. Because most elbows are around 30 feet worth of fitting. So for every 30 feet you're adding that length of duct. So, I shortened my duct runs. Yeah, how many fittings did it take to do it? Because you probably lengthened your duct runs, okay? So we look at those fittings, we figure out what their equivalent lengths are, And we add those up. So at the end of the day, we don't have a pressure number, we have a length. But you can do a little bit of math, right? The formula is available static pressure, how much power I have left, times 100. It's per 100 feet. Divided by that total equivalent length. And it turns out, the math works out that that will give you a friction rate. That will give you your ductulator number. And if you use that to size your ducts, things should work. You're designing not to make the ducts happy. Point one's great. Point one is the sound is mostly under control until the velocities get super high, right? Or the airflow gets super high. It's economical, right? You're using relatively small ducts for the airflow. It's awesome. Problem is you just can't get away with it in most modern residential systems, right? A gentleman who did a presentation at this symposium a couple years ago, Rick Sims, likes to talk about the war on sensible. I love that term. However, it's a whole nother topic that we're not going to get into. There's a war on blowers also happening, right? Every damned thing we do to our systems is making it harder to move airflow. And point one just can't keep working. So, you know where this is going. If I know what my blower power is, I can attack the other side and create the balance I want, but I'm gonna have to adjust things. I'm gonna have to adjust that friction, okay? So I try to go out of my way. I actually taught a thing here a couple years ago about unteaching people things. The key to telling people that they're wrong is to start with, you're right, okay? And so when it's true, by the way, it's very effective. So when I have somebody who's telling me that, no, those duct sizes are too big, I will say, well, you're right. These aren't 0.1 ducts. And 0.1 used to work. Well, most of the time anyway. Because back in the day, a 2-ton house was like, what, here in Florida, what are you gonna, a shed, right? What do we put a 2-ton in, right? We had a special order, a 2-ton, right? Which, not true, but special ordering 1.5 tons in Texas, very real, right? Back in the day. Now, that 2-ton unit is covering a 2,000 square foot house. Look, most of the resistance is in the fittings, but that's just a longer run, right? Filters used to keep the cat out of the furnace, right? The job of the filter used to be to keep the coil clean between maintenances. That was it. Now we're cleaning the air, or at least attempting to, and it creates more resistance. Like, that's not a surprise to a room full of HVAC people. And have you looked at a coil lately? Good Lord, right? 50 years ago when 0.1 was working, right? They're like 3 times the size, and the spaces between the fins are tighter. It's harder to move air through a modern coil. And oh boy, the unit location. It's called central air, not corner air, damn it, okay? Get that thing in the middle of the house where it belongs, and we will have an easier job. More on that to come. And so if these things, when they were like this, when there were little houses and throwaway filters or non-restrictive filters and tiny coils, 0.1 worked. It did. But we've been using 0.1 for so long, we're sort of the boiled frog, right? If you haven't heard that expression, it's the temperature goes up slowly and you don't notice the temperature's going up and it eventually kills you. Things just got worse so slowly that nobody really picked up on it. And the kick in the pants, this is the you're wrong, but it turns out you're right. An oversized air conditioning system on an undersized duct system has a lot of things going for it. I mean, it's terrible, don't do it. But it's terrible in a way that the homeowner doesn't complain. I occasionally get the opportunity to talk to people who are sort of bigger picture thinkers, if you will, the building science community. And a couple of things that I like to point out to them. Number one is there are very few people who get out of bed in the morning thinking, I'm gonna do a bad job today, okay? 2, this massive underestimation that many experts have of your average HVAC contractor is literally wrong. It's so wrong, it's coming back around to right again. Because what they fail to understand is that you guys are craftsmen. That is your job, to make it work. You show up to somebody's house, the homeowner is not happy, your job is to make them happy, and you have a whole set of skills that can do that, right? And so what? They end up with an overcharged system. They're not complaining anymore, they're a happy customer, and they didn't have to spend $10,000, right? Unfortunately, that stuff can kind of bleed into our everyday practices, right? Nothing's broken. Here's the other side of that coin, the message for you guys. The homeowner isn't complaining is an incredibly low bar, okay? The homeowner barely knows what temperature their house is, right? I was talking to Jim Futch last night. He had a problem customer. What did he do? He took the thermostat off the wall, went to the truck, adjusted the dial so it said 76 degrees instead of 72 degrees, put it back on the wall. Customer was loving it. That's a real thing. Half of you have some version of that story. And so using the homeowner is happy as a bar for success is where I think we mess up in the HVAC industry. We're trying to do good work. We just happen to judge ourselves using people who are terrible judges, right? We should be using tools like the TrueFlow Grid, right? We should be using tools like MeasureQuick. We should be using verifiable information to evaluate ourselves because we're the experts here, not the freaking homeowner, right? And so if I oversized a bunch of systems, if I just never changed how I did things, I'm just gonna keep putting 3 tons in this house and keep using 0.1. Man, that would work for a surprisingly long period of time in home upgrades. If we're sending techs out there to solve the frozen coil problem by adding refrigerant, which we probably are, right? So, little side note on the blower location thing. You may remember from any electrical lesson you've ever had that resistance adds in series, not in parallel, okay? When you reduce the flow, you reduce the resistance. And so when I have more flow on the left, I have twice, actually you have 4 times as much resistance, but let's not get into that. You have more resistance than you do in parallel, okay? Well, ducts are the same thing, okay? It's just a circuit, right? In fact, that's a really useful thing to remember. It's not the topic we're doing today, but a blower is a circulator, not a pump, right? The supply end is connected to the return end. It just uses this big space to connect them, okay? It's just a big circle. It's literally a circuit, okay? Minus the leakage to outside. So when you have something that's located in the middle of the house versus in the corner, what you have is a short path for that air to flow, right? That each of these outlets is a separate parallel circuit, right? And so my longest path is this. Okay, that's the longest the air has to go to get through, all the way through from supply to return, all the way through the system. Now this was designed by Manual D using some pretty run-of-the-mill numbers here. Note that those supplies are flex duct, so they're 7s and not 6s, right? They might be 7s even if they're metal. You don't know until you do the math, but if I was doing the math properly, a lot of those 7s need to be 8s because the run is longer. The friction created, remember, it's all about the friction you create. And so moving through more of that duct creates more friction. There are twice as many fittings in this path as there are in the short path. And so I need bigger ducts. I can't use a 16 on this one for my return. It's gonna have to be an 18 because I'm asking more of it, right? That is it's a pipe dream. Like you can ask your clients anything you want, but if you could just get them to understand, if you have a builder client you work a lot with, that it's central air, not corner air, right? That everybody's job gets easier. Like we don't have these giant ducts we're gonna have to find space for if you let me put it in the middle, right? We'll be cutting the airflow in half and cutting the resistance. Everything can be smaller. It'll be easier to put this thing in your house. Yeah, it's not It's not a real effective way to get that done. But anytime you can build the relationship with that builder to get them listening to you, this is one of the things that they can do to make your job easier, right? So I have some other slides on some other topics, but this is the core material, and I wanted to create a fake stopping point here for people to ask questions, if we have any. Does anybody want, did I see a hand? Nope, just some movement. Really? That's a first. Yeah, all right, Wes.
Will all of this be in the manual D?
So it turns out that for those people who are looking for rights-off training live and in person, I'm not currently doing that at the moment. My calendar is empty. And that's because the fine folks at the ACCA have asked me to rewrite the informative section of the Manual D, and I am in the process of doing that. And I have the next several months completely blocked off. And yeah, not loving that I just said that to the world, but now I'm really on the hook for it. I haven't cashed any checks yet, but now I guess I'm down. So yeah, and actually that's sort of the first thing that's going to go in the book is a similar explanation to the one that you just saw. Because, man, I can't stress this enough about just things in general. I love that it's our first instinct to teach people the math. And for those people who think like that, that's awesome. But you can understand so much of this without a single number. Yeah.
All right, so Alex, are you saying that instead of 0.08 or 1.0, we're supposed to use 0.06 now?
No. Yep. Very good. Good joke. I'll tell you what, the presentation that I was going to do, I switched it to this because the manual D work was turning out to be a lot harder than I thought. So the presentation I was going to do was going to be on the subject of how to use rules of thumb effectively. Okay? Because using a rule of thumb is an important thing when you are in the field and don't have access to software or anything else, right? And it is an effective thing to evaluate a system using 0.06 rather than 0.1 because you are more likely to be able to succeed. Like what I would rather do is use a true flow grid and forecast my system, but if I can't, I could look at my duct sizes and not use 0.1 to verify whether or not I'm in good shape, right? And so there are definitely times where a rule of thumb can be useful. The problem is eventually, as we get this tribal knowledge in our industry, that rule of thumb gets taught as the gospel. It gets taught as, this is how much air is in a duct. No.
So in your example, you have the 1 central return in the diagram.
Yep.
So if you design a system where you have like a supply and a return in each room, as long as you account for the friction of the duct, is that okay, or is it?
As long as you account for the friction.
Right.
But you are stacking the deck against yourself a little bit. If you are dealing with, you're dealing with a corner unit location, you're dealing with a homeowner or client budget that's tight and doesn't want to use the best air handling equipment, the best blower equipment out there, having individual return runs adds length in a pretty significant way, adds resistance in a pretty significant way. Not only does it add the literal length of you're adding fittings is really the big thing, but if you look at what happens in the most common fitting in the supply system, the most common fitting in here is a takeoff, right? Air is going this way, some air is going that way. It doesn't interact a hell of a lot, right? When you have a system that looks like this, but is returning air, T-bone collision every time you do it. There's some extra amount of friction that builds going back, depending on, especially if we're lucky enough to have the really big return all the way out the end and the smaller returns getting kind of sucked along the path, it's actually not that bad. But when your biggest return is closer to your unit, it's creating more resistance in that T-bone collision. Yeah.
So if you're trying to design for a dedicated dehumidifier, like a whole home dehumidifier, and you're doing a direct return, and then you're supplying the air into the air conditioner, So the dehumidifier is sucking its own air. It's got its own return. But you're adding that CFM into the ductwork. Do you account for that added CFM when you're doing the duct design? And are you worried about if it gets too big,
So
the actual dehumidified air doesn't move very well?
bonus points for the question. That's a really interesting question. Yeah, there's a lot going on there, right? I would say your biggest concern is overcoming the static pressure in the supply. Manual D is super simplified. Okay, the factor involved where you change the size of the duct and the amount of air in the duct, the amount of resistance you get out of those fittings changes a decent amount, right? And when you look at a modern system, this is a simple system. This is my example of the bad one, but this is a simple system to compare to what most modern systems look like. And so the resistance that you're dealing with is typically going to actually be much lower than what Manual D is going to give you. Manual D is going to design for, you're going to design for 1/2 inch of water column on an air handler, on a furnace. Good luck with that. And at the end of the day, on an install, if you set it to the fan speed you planned on, if you saw 0.5 on the manometer on day one with a clean filter, I'd eat my left shoe. It's not going to happen. Manual D is built with enough wiggle room that I think that the second key thing I would, because I'm making this up as I go here, the second key thing I would pay attention to is the disparity between the amount of CFM in the supply and the dehumidifier, right? So if I'm injecting 120 CFM onto a 1.5 ton system, you should change your design CFM, right? If I'm injecting 120 CFM into a 1600 CFM system, it's going to be in the margins of what Manual D is doing, all right? But your biggest point is, or your biggest point of friction, no pun intended, is going to be actually getting 120 CFM into that supply against that back pressure. Like, that will be your biggest problem. And so once you are planning to do that, your biggest problem might be that you sized all of this ductwork correctly, but you've designed a system that's going to create 0.4 inches of static. And your freaking dehumidifier can supply it, 0.3. You're not going to get any airflow, right? So yeah, I think it would have more to do with that overcoming pressure problem than the total CFM you're calculating in the airflow. Other questions? All right, let's go to bonus material. Northerners. Oh my goodness. Yeah, they sell you duct called 6-inch oval. It is not anywhere freaking close to a 6-inch duct most of the time, okay? First of all, the metal manufacturer is just kind of winging it, right? You get one that's doing 3-inch, you got one that's doing actual 3 1/4, right? This guy over does the 3-inch because, we don't want it to make the sounds or whatever, so we make it a little smaller. Okay, great, you make it smaller. You know what happens when you make it smaller, right? Less airflow, right? If you actually look at the dimensions that you should have for a 6-inch duct, it should be somewhere, if it was a 3-inch, about 3 by 12, right? 3 1/2 or 3 1/4, about 10, 3 1/4 by 10. What you get is about 7 1/2. Whether it's 3 or 3 1/4, right? You're getting a 5-inch duct. You can pretty much take a look at all that oval ducts going up the wall and just size it to the next one up as a way of anticipating this. But it's another example. I don't know who considered. I have a theory that they took a 6-inch duct and hammered it into an oval. I have a theory that it's like the same perimeter. It's actually not. I've done the math. It's somewhere in between. But like originally they took a 6 and smashed it into an oval shape, and that was a 6-inch oval. Because that would be a lot closer than what you actually get when you buy those oval ducts in round size equivalents, right? We get blamed for a lot of stuff that's not really on us, right? It's not unreasonable to think a 6-inch oval would be the same as a 6-inch round. How are we doing? So we're at dead stop. Okay, well, there's a mystery. Come and find me at lunch. I'll tell you which one is better.
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community. For techs, by techs.